So the second main concept that's covered in this chapter is something called elasticity, and we have looked at this in a very simple form in the past when we talked about Hooke's law, and we said that the force that a spring is going to exert is going to be equal to the spring constant K multiplied by how far it was stretched over. Here we're looking at an object that may not necessarily be a spring, but is going to have some spring-like behaviors. Everything is going to stretch just a little bit. We know that if we hang a weight off of this object, it's actually going to deform by some distance delta L. That's analogous to the change in x right here. And then this number right there would represent what before we called the spring constant, which is how much an object resists the stretching of it. It turns out that in reality that this proportionality, saying that the force is equal to some k multiplied by some change in length or change in x, this linear relationship is only true up to a certain limit. So here we're plotting force against the change in length, and this elastic region here is where this equation is true. Once you have stretched a spring or an object past that point, it enters this region right here called the plastic region, and in that region then the object will not return to its original shape. That would be the case right here. If you applied a force to a spring and you just let it go, it's going to return to its original shape. There is deformation going on here in this plastic region. And finally, as you stretch an object further and further and further and further, at some point the amount of force that it pulls back on is not going to go up anymore. It's going to start to go down, and that is very, very close to the object's breaking point. So we're going to expand on what we know of with Hooke's law by talking about elasticity, stress, and strain. So we're going to define two quantities here, stress and strain, which are related to the elasticity of a material. We'll consider stress to be the force that is applied to an object divided by its cross-sectional area. So if you think about pulling on two objects with the same amount of force, say a very thin wire with a small cross-sectional area, and then a very, very thick wire with a huge cross-sectional area, obviously you're going to greatly stress the very thin wire, and not so much stress the thicker, larger area wire. And then we'll talk about the object's deformation with its strain, which is going to be how much it changed its length relative to its original length. If you pull on an object and you change its length quite a bit relative to its original length, then you've strained it quite a bit. So the change in length is going to depend not only on the force, it's also going to depend on the area, as well as the material of which the object is made. That's related here in the strain. The ratio of stress to strain is this thing called Young's modulus, which the book nicely gives the symbol E. I learned the symbol Y when I was learning this. Y makes more sense, but I'm sticking with the notation of the book. And what that does is that lets us relate the object's stress to the strain. If you remember Hooke's law right here, force is equal to K multiplied by some change in length. If now we write that an object's stress is equal to this constant Young's modulus multiplied by the strain, you can see that I have some force right here, and here I have a force divided by area. Here I have a constant that is depending on what the object is made out of, how stretchy it is. The same is true for Young's modulus. It depends on the material of which it's made out of. And then the strain right here, how much it is deformed by, is very similar to Hooke's law. So Hooke's law is kind of a generalized version of this equation right here. Obviously, Young's modulus has been measured for many materials. If you look at table 9.1, you'll see quite a few of those. And since you're already familiar with Hooke's law and how to look up a spring constant and solve for deformations, I'm not going to work through an example, but please do be familiar with example 9.10 in the book, which works a Young's modulus problem. We'll talk about two types of stress here, the first of which is tensile stress, in which cases the forces that are acting on an object tend to stretch it out. If we consider a rod sticking out of the ceiling and I pull down on it with some force F, then the ceiling is going to pull back on me, and these forces tend to stretch the object out. Simply definition of tensile stress. We can calculate what this stress is by measuring the force and measuring the cross-sectional area of the object. Compressional stress is the exact opposite. In this case, rather than trying to pull a steel rod apart, compressional stress tends to act inwards towards the object, compressing it or trying to make it smaller. So we have the weight of all that stuff up there, and then it's being supported down here by a force. These forces tend to make the column a little bit shorter. If we know the cross-sectional area and these weights right here, we could calculate how much stress is being applied to the column. And if we knew how much the column had changed length from its original state, then we could actually calculate the strain on these columns. Another type of stress is going to be shear stress, which is a little bit different than the types of stresses I've been talking about earlier. One last related type of stress I want to talk about is when a force is applied to an object and another force is applied to another face of an object. This is called shear stress, and it tends to deform the shape of an object. So we can say that this delta L here is going to be perpendicular to its length. Now, unlike the past two tensile and compression stresses where I was able to write that the stress is going to be equal to Young's modulus multiplied by the strain, with this type of shear stress, I have to write that the stress is going to be equal to this shear modulus G multiplied by the strain. E and G are similar and in some ways related, however these guys are different, and in general this G value tends to be about a half to a third of Young's modulus, the shear modulus does. If the stress on an object is too great, then the object's going to fracture, whether you pull on it too hard and it fractures, whether you compress it too much and it fractures. Think about stacking up a whole bunch of boxes and the top box is way more than the bottom boxes. We'll get a fracture there. Or also we could have the same type of thing with shear stress, where you just shear a bolt right out of a hole. So we know if the stress is too great, it's going to fracture. And the good thing is we've gone ahead and we've measured the ultimate strength of materials. You can see this in table 9.2. This table tells you the tensile, compression, and shear strength at which an object will tend to fail at. So it tells us the stress that it will fail at, and it tells us that in newtons per meter squared, obviously depending on the force and the area. So what we can do is we can go ahead and we could calculate the forces that are on an object, and if we know their cross-sectional area, we can calculate how much force is on a cable, look it up in a table, and be able to tell if that cable will break if we put it into a suspension bridge. We could also say we don't know what these forces are, but we know the type of material that we're working with, we know the Young's modulus, and we also know how far this object has deformed and how far and the original length of the object. So we could go ahead and calculate what the stress is simply by using the strain. A good rule of thumb is to go ahead and calculate out what you anticipate the stress would be and leave a buffer factor somewhere on the order of 1/3 to 1/10 of the ultimate strength of the object. If not, you need to either decrease the forces on that particular item or you need to beef up the area of that item. If we look at a horizontal beam, it might tend to sag even under its own weight, or you could even imagine, somebody walking on top of that horizontal beam. A horizontal beam is actually going to undergo both tensional stress and compressional stress. If you think about all of the atoms of this beam right here, they're being squished together from the neighboring beams. There is going to be some compressional forces on the upper side of this beam right here. If you look at the bottom side of this beam, it's tended to be stretched out. It's been deformed. It's longer now, so it's undergoing tensional stress. So when looking at a beam, we can have two types of stress on it, and we want to make sure, of course, that both of these are less than the ultimate strength of the beam, both in compression and in tension, because the ultimate strength is going to be different for compression and different for compression and tension, even though it's the same type of beam. Lastly, there are some shear stresses going on within the beam, but we'll ignore those for right now. So while we're talking about fracture, there was a walkway in Kansas City that collapsed and killed about 100 people. It was engineered properly, however it was built wrong because the people that were building it didn't understand the simple physics that was behind all of it. The walkway was originally supposed to have two supporting beam, or originally supposed to have only one supporting beam that was 14 meters long and have single attach points for each walkway. However, during the installation process, they decided that it was too difficult to install the long beams, so they installed two shorter beams, now with two pivot points. The difference really doesn't appear to be major until you consider the forces on the bolts, which are the pivot points here. In the original design, each pivot point only had to support the weight of that particular walkway. The weight of the walkway below it was supported by its own pivot point. However, by splitting the single beam up into multiple beams, now each pivot point has to support not only the weight of its walkway, so mass times gravity, but the weight of the walkway below it. So this pivot point here is now supporting 2 times the mass times gravity, and the one above it is going to support 3 times the mass times gravity, which eventually exceeded the ultimate strength of the pivot point, causing causing the walkway to fail. It was ultimately the Romans that developed a semicircular arch about 2,000 years ago, in addition to making other vastly important engineering feats. But rather than having a single stone or a single board or brick trying to span a space, we know that there's going to be compressional stress up here and tensional stress up there. Eventually, you'll get a space so wide that this thing will fail. They developed a semicircular arch in order to circumnavigate this. So what the Romans did was they actually cut their bricks such that they were under compression, and when the weight of some bricks that were directly above the arch pressed down on this stone right here, then the compressional forces redirected that weight off to the sides here, and eventually it's all supported over here simply by using the fact that these bricks are all under compression to redirect where the weight is supported from. So fairly ingenious. It turns out that the shape of the arch actually also makes a difference. If I consider two arches with different shapes and I apply a force downwards here, if I look at kind of the angle that the arch is at that given point, it's going to take some amount of horizontal force to keep this part of the arch from moving away. However, if I build my arch to be much steeper, the angle is also steeper, and kind of conceptually you can see that this horizontal component is going to be much smaller, which, if this arch is not part of a bridge and you need to support it externally, lowering the forces is going to be good when we're talking about stress, fracture, and strain. It simply changes the way that an object looks. Whether that's pleasing or not, that's up to the architects. Domes are very similar to arches. They simply span a two-dimensional space and are just a little bit complexer when it comes to the math, but all of the theory that we've talked about for arches applies for domes as well. And the summary?